This time, we are going to show one-to-one onto linear transformations and also insert the idea of isomorphism, because isomorphism rather can only be determined once we can establish one-to-one and onto linear transformations at the same time. We have this two 3x3 matrices here, and it's very important for us to do that because once we know the type of matrix that we have, as mentioned, we have 3x3 matrices here, we can say, of course, that's m by n, because our transformation is defined as r to the n to r to the m. Okay, in short for this, the linear transformation is defined as r3 to r3. Okay, so this is very important in a sense because we're going to use the idea of the domain and codomain sets here in showing whether a linear transformation is a one-to-one linear transformation. Okay, we're going to start with one-to-one. We need to show that the kernel of T of these two matrices is equal to the zero vector. Okay, the set containing the zero vector. And what is this zero vector comprises? This is an element of our codomain here. So our zero vector is an element of R3, hence it should be in this form: 0, 0, and 0. Okay? Aside from this, we also need to show that the linear transformation is on 2, and we can only establish that by showing that the dimension of your domain is equal to the dimension of the basis of the range of T. Now the domain is this here, and the dimension of R3 is equal to 3. And we're going to show the connection of that later. Okay, that's why this is very important. Okay, this definition of our linear transformation using by the matrices is very important. So let's start now when solving a one-to-one and onto linear transformation of the first matrix. Now to do this, we shall start with getting its reduced row echelon form. Okay, why do we need to come up with the reduced row echelon form? Okay, that reduced row echelon form is very important in determining not just the kernel, but of course the idea for the basis of the range, because the basis of the range, as discussed in the previous videos, is equal to the column space of A. The column space of A contains the pivot columns or the columns with the leading one, and we can only say a leading one once we can establish a reduced row echelon form. Let's start with the kernel again. Of course, the kernel should satisfy this linear transformation. You have here AV is equal to the zero vector. Again, the zero vector is the zero vector in R3. How about the vector V? Vector V is an element of our domain as well. So we can say that the vector V is equal to the components V sub 1, V sub 2, and V sub 3. Okay, so we are going to use that later. But again, let's start with the reduced row echelon form. I'm just going to copy it first. 1, 0, 0, 0, 0, 1, 0, 1, 0. Now the reduced row echelon form of this matrix is just very easy to be determined. You simply need to interchange row 2 and row 3 so that these two will be considered as leading ones. Because if we're going to stick with this, this is a leading one here, but this is not yet a leading one. So we're going to interchange them. You have 1, 0, 0, again 0, 1, 0, 0, 0, and then 1. And hence, that's your reduced row echelon form of your first matrix, which will again be used for the kernel and the range respectively. Now with this, we're going to solve for vector V that satisfies this condition. You will have here 1, 0, 0, 0, 1, 0, 0, 0, 1. And by the way, if you have your reduced row echelon form, it's just very easy to solve for the components of your vector V and equate this to the zero vector in R3. Because once you have your reduced row echelon form, you will get V sub 1 being 0, V sub 2 being 0, and V sub 3 being 0 as well. So the vector that satisfies the definition here earlier is the zero vector in R3, 0, 0, and 0. And that vector V is the only element for the kernel of T. It's a set containing the zero vector in R3. Now, once we reach this, this is the condition for the one-to-one linear transformation. So when kernel is equal to the 0 vector itself, this is automatically a one-to-one linear transformation. So we're done with this. Now let's proceed to the identification of an onto linear transformation. As mentioned, we shall use the same reduced row echelon form. We have 1, 0, 0, 0, 1, 0, 0, 0, 1. Because we are going to come up here with the basis of the range and the dimension of the range. So we have here 3 columns with leading ones. Or in short, we have 3 pivot columns here. These 3 pivot columns corresponds to the 3 original columns of your initial matrix. In short, the basis for the range of T for the first matrix is the set containing the 3 columns of our initial matrix, 1, 0, 0, 0, 0, 1, and then 0, 1, 0. This would mean that the dimension of the basis of your range, as this declares the number of elements found, or vectors found in the basis, is equal to 3. Now, let's connect it to the dimension of your domain. This is your domain earlier. The dimension of the domain is also equal to 3. And with this, since the dimension of your domain is equal to the dimension of your range, or the basis of the range of T, which is 3 equal to 3, this linear transformation using first matrix is also an onto linear transformation. Okay, since we have determined that the linear transformation defined by the first matrix being one-to-one and onto, though this is not part of the headline there, let's connect them. We can say that the linear transformation is an isomorphism because it what do you call this one? It satisfies both being one-to-one and onto linear transformation. Okay, let's go to our second matrix, as I believe this would need more spaces. Yeah, since this needs a lot of steps for us to determine its reduced row echelon form. So we copy here 1, 2, 3, negative 1, 2, 4, 0, 4, and 1. We already have a leading 1 here. So let's make this 0. Simply add row 1 plus row 2 for a new row 2. And then we will have here, okay, so you will have still 1, 2, 3. This becomes 0. 2 plus 2, that's 4. 3 plus 4, 7. This is still 0, 4, 1 here as well. So next here is to multiply 1/4 to your row 2, so that this would be a leading 1. Okay, so let me just separate this so that it will not be confused with the other steps. This is 1, 2, 3, 0. This is 1, that's 7/4. This is 0, 4, and 1. Next, to make this 0, we are going to multiply negative 1/4 to our, it's already, yeah, negative 4 rather. Negative 4 to row 2 plus row 3 for row 3 to make this 0. So you'll have 1, 2, 3, 0, 1, 7/4, 0. Negative 4 times 1 is negative 4 plus 4, 0. Negative 4 times this is negative 7 plus 1, so you have negative 6. To make this leading 1, simply multiply negative 1, 6 to your row 3 for a new row 3. Okay. So this would mean 1, 2, 3, 0, 1, 7/4, 0, 0, and then 1. This is still the row echelon form. And of course, you could now determine relationships to or solve v sub 1, v sub 2, and v sub 3 even with just this. But then again, we will be using the reduced row echelon form as well on our range. So let's just simply continue. Let's make the 0. Let's make the 0 as well. So you're going to multiply negative 7/4 to your row 3 plus row 2 for a new row 2, and negative 3 to your row 3 plus row 1 for a new row 1. 1, 2, 3, Sorry, it's no longer 1, 2, 3. Let me start at the bottom. 0, 0, 1. So 0, 1, negative 7 fourths times 1 is negative 7 fourths plus 7 fourths, 0. Okay, next. This is 1, 2, negative 3 times 1 is negative 3 plus 3, 0. This is still 2 because this is 0. Once you multiply negative 3 to that, it will not change its value. And finally, negative 2 to our row 2 plus row 1 to make this 0. Okay, so the final form of our reduced row echelon form is in this manner. 1, 0, 0, 0, 1, 0, and 0, 0, 1 still. So similar to the previous matrix. But of course, let's establish it here independently or separately. You will have to solve for the kernel first. So multiply this to v sub 1, v sub 2, and v sub 3. Equate to the 0 vector. You will have v sub 1 being 0, v sub 2 also 0, and v sub 3 also 0. Therefore, our vector that satisfies this here. Okay? So, 0 vector in R3. Hence, the kernel of T is the set containing the 0 vector in R3, and then this is automatically a 1-to-1 linear transformation. For our onto linear transformation, we still have the same linear transformation declared here, so the dimension of domain is still 3. Okay? So the dimension of domain is just 3. Now the dimension of your range is equal to the column space of your base column space of A, or equal to the basis of the range, or for the range of your matrix, the second matrix. Since in our reduced row echelon form, all 3 columns contain leading ones, so we're going to copy all 3 columns here as well. So you have -1, -1, 0. So you'll have here 1, -1, 0. You'll have 2, 2, is it 4? Let me do it again. 2, 2, 4, yes, and 3, 4, 1. 2, 2, 4, and then you have here 3, 4, and 1. So we have here 3 different vectors. So the dimension of your range is also 3. Being this equal to each other, we can say that it is an onto linear transformation as well. Now, it's an onto, it's a 1-to-1 linear transformation. Hence, the linear transformation defined by the second matrix here is also an isomorphism. That is how we show 1-to-1 linear transformation, onto linear transformation, and the isomorphism for using these 2 3x3 matrices. We still have one more pair of matrices that will be for our last video in determining 1-to-1 and onto linear transformations. Just for this, thank you very much for watching.